motivation behind the FinFET structure. We have also discussed the different fabrication technique required for FinFET realization. So in the last class, specifically we have discussed subtractive fin. We have discussed uh, replacement fin, and we mentioned that replacement fin is important if we want to realize different material, I mean fins made of different material. And also we have discussed SY fin, and we mentioned that in SY fin one of the advantage is the variation of fin height is very minimum, because we can have like the foundry is defining the active layer of the silicon thickness. Okay, so that thickness usually doesn't change much, whereas in bulk silicon fin, you realize the fin height by edge back technique of oxide, you remember. So there might be variation in oxide etching over the wafer, and that might give you different fin heights or variation in fin heights, which is very minimum in case of SY technology. Now if we talk about other uh, other changes in or other differences in SY fin versus bulk silicon fin. Okay, one of the advantage we mentioned that fin height is lower here. Okay, other differences are SY wafer is expensive, okay, compared to that of conventional silicon wafer. Uh, Third thing is it is heat dissipation through SY is difficult. Okay, heat dissipation is difficult because in silicon fin, what we you remember what we do, we have silicon fins which is connected with silicon, right? And then there is buried oxide. So buried oxide is I mean sorry, there is oxide, and we have edge back and realize this height of the fin, right? Now the thing is, this fin is connected to silicon, bulk silicon, so heat can go here and dissipate, right? Um, However, in case of SOI fin, the structure is like this. Here we have bulk silicon or handled silicon. On top of that, there is buried oxide, and on top of that, there is silicon fin, right? Now this is completely isolated from the handle silicon because there is a box here or buried oxide here. So it is difficult for the fins to dissipate heat in case of SOI. Okay, so that is a disadvantage if you use SOI fins. Number 4 is in case of SOI fin, parasitic BJT is not there. Okay, what is parasitic BJT? Uh, if we look, say from the side walls, okay, so we have, um, if we look side wall, so this is my fin, okay, and of course this is the gate, which is little bit taller, right, and around that fin, and of course this is the extension of the, so say this may be source, this may be drain, okay, and uh, this is your silicon, you see, I mean uh, so uh, this is your silicon, this is silicon, and also this is connected to uh, bulk silicon, right, so this is also silicon. So you see here, this may be your N plus and N plus, and this may be your P. So you see there is a BJT underneath, okay, although we want uh, currents to flow, okay, like this between source and drain, but there is a parasitic BJT. If you look carefully, this kind of parasitic BJT is also there in conventional MOSFET, right? Say in conventional MOSFET we have N plus and N plus, okay, we have gate oxide, sorry, and this is p-type substrate. So this parasitic BJT is also there in conventional MOSFET as well, right? So this parasitic BJT might turned on depending on your temperature, depending on the voltage, okay. If somehow um, this junction becomes more than 0.7 volt, okay, this parasitic BJT might turn on. So what you have to do, you have to make this doping much higher. If you make this P doping higher, so that will prevent, because you see then the base of the transistor is heavily doped, so that will prevent this transistor to act properly, right? So this, but that is an extra step you have to do for increasing the doping concentration of the substrate, right? So but this parasitic BJT is not here in SY, because the fin is completely isolated. You see, fin is not connected with silicon. Here fin is connected, fin is on top of bulk silicon. There is no isolation between the fins and the silicon. Here you see fin is connected to silicon, right? So through this substrate it can have a parasitic BJT, but which is not there in case of SY substrate. Now also here epitaxial growth is difficult. What do I mean by epitaxial growth? You remember we have discussed, like say I have a silicon fin, okay, in case of bulk silicon, and I have a oxide, uh, I have an oxide layer, so I can etch, okay, I can etch and uh, reduce the silicon height, right? So reduce the silicon height, so this is my silicon, and then we can have like epitaxial growth, uh, maybe to realize different scene. So this is my oxide, okay, different material fin or fin of same silicon but different doping and all that, okay, uh, depending on in which purpose you are to use it. So This is not possible in case of SOI, because if you etch the silicon, then the entire fin might go, right? So there is there only box layer will be there. This epitaxial growth is difficult in case of SY fin. So if we uh, see what are the plus and minus once more, we can have like so fin height variation is lower here. So this is SY is scoring. SY wafer is expensive, so that's going against SY fins. Okay, heat dissipation is difficult in case of SY. It is going against SY, but parasitic BJT is better. Okay, so parasitic BJT is better in case of SY compared to conventional silicon fins, and also epithelial growth is difficult. So it has plus and minus as far as the SOI fins are concerned compared to bulk fin. Now, another point I would like to discuss is a few more points. In fact, now one of the thing is the next generation fins will be taller and thinner. Okay, taller and thinner. Next generation by what do I mean by next generation? Next generation means next node, maybe, or next future nodes. So maybe I have a 22 nanometer process and I have realized a fin. Now if we go from 22 nanometer to 14 nanometer process, say for example, then the fin should be thinner and fin should be taller. Why it should be thinner? You remember we have discussed that if we have discussed that example of pipe. So I have source, I have pipe, and I have drain, right? Now, so this in the next generation, okay, or future node, what will happen to get better control? We need to reduce the pipe diameter, right? That is what one technique. One is reduce the pipe diameter to control the flow from source to drain. Another is to have like better gate structure, right? So one is better gate structure, and the other one is reduced pipe diameter. Now if we go from one node to the next node, so we have to make the fin thinner. Okay, if we can make fin thinner, we will have more control from the gate side, right? So we have some rule of thumb values. They are like this. So if we have a double gate fin structure, okay, we have gate 1 this side maybe, and we have gate 2, right? And the top we are not using because it is a double gate structure. In that case uh, TSI, that is the thickness of the fin, okay, roughly should be of the order of 2 by 3 LG. LG is channel length, right? So this is in case of double gate. So these are some rule of thumb values. Okay, what about triple gate? In case of triple gate, we will have gate all around, right? Now gate from all three sides. Okay, if the gate is from all three sides, then TSI, that is the thickness of the fin, maybe if you do of the order of LG, that will be okay. Okay, so this is tri-gate structure. what about gate all around? So in case of gate all around, okay, TSI of the order of 2 lg is good enough. So what I try to convey is through gate structure we can improve the situation, or we can improve the control from the gate side, and through by thinning the fin. Okay, but you see, if we have better control from the gate through gate structure, the thinning part may be relaxed. Okay, so you see, in case of tri-gate, we can get with thin fin thickness of around Lg. Okay, however, the same gate control we can get in double gate, but we have to make the fins thinner, 2/3 Lg. In case of gate all around, this is much more relaxed. Even if we do 2 Lg, the thickness of the fin, we can have like same gate control. Okay, so next generation node, if we maintain the gate structure, we need to make the fins thinner, right? What about taller? Taller fin means you can have more current. So taller fin will give you more current. Okay, so more current. So that is why taller fin is also important. Okay, so for ion proportional to 1/Lg, okay, and also proportional to H fin. So if you may make fin thinner, make fin taller, ion will be more. Okay, so you see, in next generation nodes we have to make fins thinner and taller, although it is difficult to fabricate, right, if you go for much thinner structure and much taller structure. So that's one thing I thought that I should convey to you. Another important parameter is fin width. Okay, those of you have done uh, those who have done the design of your circuit in cadence or synopsis, okay, and the layout, you probably know that in case of ordinary MOSFET, you can have like any width you want. Okay, the L is defined for that particular process. Say I am using 22 nanometer process for any bulk silicon based MOSFET, the minimum gate length will be then 22 nanometer, right? But the width, you can use any width you want. I mean, any width means, of course, there is a limit, but in the higher side you can use any width you want, right? But that is not true in case of fin. In case of FinFET, that is not true. How we calculate the width of the fin? The usual procedure is 2H fin plus W fin. So if so this is my fin, this is my W fin, or basically the what should I say? So this is thickness of the fin, or TSI. We are representing TSI, right? So we can write here TSI also, right? TSI. So TSI is the thickness of the fin, but width of the fin, W is basically width of the fin is 2 H fin. This is my H fin. Okay. How I'm getting this formula is if you look carefully, it's not difficult, because in conventional FET, how to draw this? So you have So this is my conventional MOSFET. Okay. So this is N plus, and this is my gate oxide, right? Sorry. Right. So this is gate oxide. So this is, say, source, drain, and so on. So this is my LG, right? And this is my W. So if you now uh, if you now fold your W, you see, if you fold your W, okay, like this, if you fold your W, what will happen? You get a fin like structure, right? So you see, if I fold it, you will, if I fold it, then I will get a fin like structure. So what will be the, then what will be the fin width of the MOSFET, or width of the FinFET? Width of the FinFET will be H fin this side, H fin this side, and TSI. So these three will make your width of the fin. So H fin, 2H fin plus TSI. That is the width of the fin. I hope you understand. Okay. Now the thing is, we can't have like, now we can have like multiple fins. So we can have width, depending on the number of fin, we can have. So if there is n number of fins, together we have clubbed, then that means will have, this is the width of the fin. So width of the fin is like fixed value. It is not like any value you want you can get it. I mean, you can change the number of fins, and you can get width of one fin, two fin, three fin, four fin, and so on. But if you want to realize 2.5 fin, it is very difficult to get. You will not be able to get, because you can't change. Unlike bulk silicon based MOSFET, you can't change height of the fin here, right? You see, you can't change height of the fin, you can't change TSI, right? For a particular process, you can't change TSI, you can't change the height of the fin. So your width of the fin is like a fixed value. Of course, you can use multiple fins and change and get higher order width. But the thing is, it's not like a value what you exactly want. It will be like that. Okay. Although there are processes, what you can do, you can, um, instead of having a fixed fin height, you can have like fin of different heights. Okay. So this is a fixed height fin. Okay, but you can have like different edge back, um, because you remember the height of the fin depends on how much you are etching back your oxide. So see here, you can get like different height, fin of different height. Okay, but of course this is difficult to control, because then you have to etch fins of different height at different time. Okay, because you have to open up certain fins, you have to edge them, then you need to close the fins which you have already edged, then you need to realize the fins which you haven't edged, and so on. So that's very complicated, but it is doable. Okay. Now the last thing I would like to discuss is orientation of the fin. Okay, fin orientation. So what is fin orientation? Fin orientation is, you see, fins can be realized in different orientations uh, in your wafer. So fin orientation. So I have a wafer like this. So those who have seen wafer, they know there is a flat portion in a say in a silicon wafer or other wafers. Okay, so this flat portion. So there might be one flat portion. There might be multiple flat portions. They have like different meaning. Okay. If you don't know, you just search it in the net. You will get information what this flat portion means and what the additional flat portion might comes 90 degree of these or a certain angle and so on and so forth, so that you can get information. Okay, now just to, I would like to mention very briefly, say this flat portion represents 110 plane. Okay, now the thing is the fins might be of different orientation. So say the fins might be like this. Okay, we get here. So in that case, the channel surface is along 110, right? If it is like I don't know, maybe in the orientation of 45 degree. Okay, so then so this may be 110, this may be 100 and so on, right? So this direction then, so and so on. So you can, what I am telling you, you can change, you can get different the crystal orientation or different crystal plane depending on the orientation of the fin. So it has some pros and cons. So depending on in which orientation your fins are, your crystal plane will be different, and crystal plane will change your mobility of your carrier. Okay, depending on the orientation, one can have like different electron or whole masses. Okay, and hence that will change their mobility. So just wanted to mention, like if we have I mean, if let me plot. um, so this is my T silicon. Okay, nanometer scale, and this is my mobility. Okay, this may be mobility of sorry, mobility of electron, this may be mobility of hole, and so on. So so in case of um, electron, the mobility is higher when you go like when it is along 100 plane. Okay, compared to when it is 110 plane, right? That is reverse in case of uh, holes. In case of holes, it is 110 is higher and 100 is lower. Okay, so you see, if we can tactfully make uh, n-type FinFET with 100, we will get higher mobility. And if we can make FinFET of p-type FinFET with 110 direction, okay, channel direction, then we will get higher mobility. Again, it's very difficult to do. Okay, but this is just a thought, right? What else? I think I will stop FinFET here. Do you have any questions on FinFET? Any doubt? Otherwise, we will start uh, a different chapter. Have any doubt about FinFET? Anything you want me to discuss again?
Yes, sir.
Yes.
Sir, I have small doubt that
Yeah.
in the middle of source and drain, where
Right.
the gate is covered. Underneath the
Yes.
gate, is it a P type or some intrinsic? I don't know. I didn't understand that.
No, it's the substrate doping.
Yes, sir.
It's the same as the substrate doping.
Okay, it is okay. Okay, sir. The underneath substrate.
Yeah, yeah. But if you need like additional doping in the substrate to reduce the parasitic effect, then you have to dope underneath that gate portion. I mean, no, not underneath the gate portion. Let's put it this way: underneath the, I mean, deep in the substrate, a different doping level, little bit higher doping level, so that you can reduce the effect of parasitic. Otherwise, it is like uniform doping are just underneath the gate portion and also deep in the substrate. Okay.
Okay, sir. Thank you.
Anything else? Right. So what I want, um, as I'm continuing this advanced device discussion. Uh, I mean, I don't follow any specific pattern which one to discuss when, as long as they make sense, we discuss them. So as we have started, I mean, in earlier classes, probably we have discussed FinFET much later, but I thought that I will discuss it this time because it is in line with IC roadmap. Now what we are going to discuss, we would like to discuss some advanced devices. For example, we would like to discuss now Hemt. Okay. So if you look at the syllabus which I have provided to you, Hemt is the part of the syllabus. Okay, along with FinFET. Hemt. Uh, have you gone through Hemt before? Any of you? Was it covered in any of your previous syllabus? No? Okay. So Hemt stands for high electron mobility transistor. So in next 2-3 class we will discuss Hemt and also we will discuss HBT, heterojunction bipolar transistor. So these two advanced topic we will cover before we move to something else. Okay. So by that way we will finish everything associated with IC roadmap and how the advanced devices look like and all that, why we need these advanced devices and so on. So the motivation behind FinFET you understood, I guess. Now the thing is, as you as you saw that FinFET, you can realize um, even on silicon. Okay, primarily it's on silicon, but you can realize other material based fin also. But it is an extension of the conventional MOSFET in a sense ki we would like to improve the leakage current effect. I mean, we have to reduce the leakage current or we want to get better control from the gate side, and we need multiple gates, and that is how this FinFET technology developed, right? Now the thing is there are other short channel effects we mentioned. One of the short channel effects was mobility degradation. You remember? We discussed that if we move to higher nodes or next generation node, mobility degrades. Okay, and there are different thing you can do to improve mobility. Uh, So one thing was mobility degradation, and another thing was punch through. We have discussed in short channel effect. Can't remember we have discussed punch through or not, but we have probably. So in punch through, what happens is you see we have this n plus and n plus, and we have this So underneath the gate there is depletion region because of this whatever uh, whatever voltage you are applying from gate side, right? So you will have channel and you will have depletion region, right? But so here there will be depletion region, right? So that is because of the voltage you are applying at the gate, and also there is depletion region underneath the source and drain, right? There is depletion region here as well. Now the thing is, this is in case of long channel, but in case of short channel, the gate and the source and drain are very close, and it might happen, you remember this depletion region might match each other, okay? So then you will lose control from gate. So what you do to avoid this, so this is known as punch through, okay? Because you have depletion region from source side and drain side, they are basically merging, okay? And you lost control from gate because there is hardly any depletion region because of the voltage you are applying from gate side. Now the thing is, you can reduce this punch through effect or you can minimize it if you have like if you increase this doping concentration. So we can increase the doping concentration, right? So if we increase the doping concentration, then this spreading of depletion region in the substrate will be lower, right? So you will then have depletion region much lower. Now if you increase this doping concentration, that will in turn affect the mobility, right? You remember, if we increase the doping concentration of the substrate, that will degrade the mobility. So what people do, sometimes they do halo implant. Halo implant means implant near the source and drain. So here they make things P plus, okay, instead of whole substrate. If you So this is known as halo implant, okay? So selected portion near source and drain, you implant additional, you make this portion additional doping, okay, or higher doping to reduce the spreading of the depletion region from source and from drain, okay? Anyway, but if you increase the substrate doping, that will degrade the mobility. Now the thing is, how to improve this mobility? We discussed a little bit very briefly, like we can use strained silicon. Other things also you can do which will improve the mobility. That is the structure we are going to discuss in high electron mobility transistor or Hemt. In Hemt, we can achieve, as the name suggests, we can achieve higher electron mobility from the transistor, right? Now, behind this Hemt structure, or the way we realize this Hemt structure is by generating a heterojunction. What is heterojunction? Heterojunction is a junction created by two dissimilar material. So junction created by two dissimilar material, okay? So if you have a junction of two dissimilar material, you will get notch at the junction, okay? What is notch, we will discuss in a minute. So let me repeat it once more. So the Hemt structure usually realized by making heterojunction. So what is heterojunction? Heterojunction is junction formed by two dissimilar materials. Now if you make junction of two dissimilar materials, there will be notch at the junction, okay, or at the interface. Why I'm saying that? If we draw the band diagram of two dissimilar materials, we will see that very clearly. But this um, notch formation or this heterojunction formation came from the concept of MOSFET itself. Okay, if you think about MOSFET, in MOSFET also there is heterojunction, and in MOSFET also there is notch. How? So I have like, so this is my silicon oxide interface. Okay, so this is my oxide, this is my silicon. So if you apply bias, right, it will be tilted. So depending on, so if it is like, so if it is NMOS, let's put it this way, if it is NMOS, we will apply positive gate voltage, so the oxide will be tilted. Now the thing is, so say this is my Fermi level in the in silicon, so the conduction band will, depending on the biasing, the conduction band will go very close to or maybe lower than that of the Fermi level. Okay, right, at the bulk it is p type, but near the oxide silicon interface it becomes n type. You remember? Now the thing is, if you look here, this particular point, this is nothing but a notch. Okay, this is a heterojunction of oxide and silicon, and it is a notch, and in this notch there will be electron, and those electron is moving away from the paper or moving inside the paper, depending on which side is source and which side is drain, right? So this is a notch and electrons are present in the notch. Now the thing is, there is degradation or mobility, because you see we have discussed these electrons often talk to these immobile ions, right? These immobile ions which are present near the channel, just underneath the channel, these electrons will talk to them, okay, or will interact with them, and their mobility will degrade. Okay, right. So now if we can somehow um, reduce this interaction, then the mobility of the transistor will improve. Okay, so if we can reduce the interaction between the carrier electron or hole with these immobile ions, then the mobility will improve. That is what we exactly do in high electron mobility transistor. Okay, precisely we will discuss here a basic high electron mobility transistor, but there are other structure also of different um, uh, using different working principle and also on. So here we will discuss a very basic Hemt structure to give you the idea how this Hemt structure look like and what is the working principle. Now the reason we are discussing this in this uh, nanoelectronics course, because as it is an extension of this IC roadmap, that is one part, and second part is in this notch, if this notch is very tiny, then the energy bands here, there is discrete energy bands. Okay, and in these discrete energy bands, they are very tiny, and electrons will present as a wave, particle and wave, between particle and wave. So those particle wave duality we will discuss later on when we will discuss quantum mechanics and the effect of nanostructure, effect of quantum mechanics on nanostructure. So then we will discuss. So it is already this quantum well kind of structure is very tiny, and quantum well kind of structure can be realized in Hemt. So it is directly comes in the it is directly comes under the umbrella of nanoelectronics, right? Now let me. So what is this? What is this basic Hemt structure? Basic Hemt structure is made of aluminium gallium arsenide, aluminium gallium arsenide. Okay. Aluminium gallium arsenide structure. So we use this material to develop Hemt. Okay, we use the heterojunction structure with this material and develop Hemt. So this is a basic Hemt structure. Now the thing is, what is the requirement of having this heterojunction? Because any two material if you use, it will not make a heterojunction structure, right? Now the requirement is, one of the requirement to have a heterojunction is lattice matching. So if there is not enough lattice matching, then you see there will be lot of defects, and if there is lot of defects, that defect will reduce the mobility. Okay. Now the thing is, apart from lattice matching, there is another aspect you need to uh, think. So that we will come in a minute. But let me discuss what is this x and 1 minus x. So what we usually do, we have like a gallium arsenide structure, and in the gallium arsenide structure we remove gallium and put aluminium. So in gallium, the way we realize gas or aluminium gallium arsenide, that is often known as gas, we remove gallium and replace gallium with aluminium. So you see x proportion of aluminium will remove 1 and make 1 minus x of gallium, right? Because initially we had a gallium arsenide structure and we remove x gallium to incorporate x portion of aluminium, right? Now if you remove gallium with aluminium, the radius of aluminium of the order of 125 picometer, okay, and radius of gallium is of the order of 130 or 136 picometer. So you see, when we replace gallium with aluminium, there is hardly any difference. So it will not, the adjacent atoms will not notice it much. Okay, although if you remove all the gallium, there will be a lot of strain, because you have all the gallium is replaced by aluminium, that is a foreign material. Now regarding this lattice matching, I would like to point out aluminium arsenide has lattice constant around 5.66 angstrom, whereas gallium arsenide has lattice constant around 5.65 angstrom. So depending on, even if you change x from 0 to 1, so this means x equal to 0, that is gallium arsenide the material, and x equal to 1 means entire gallium you replace with aluminium, then also you are meeting this lattice matching criteria. Okay. Now, as I said, if you don't meet lattice matching criteria, then there will be lots of defects in the interface, and that is not good for the mobility of the carrier. Now, one more thing I would like to point out is the band gap of the material. Now, this gallium arsenide is an is a direct band gap material. Probably most of you know. So this is roughly 1.43 electron volt. Okay, and the satellite value maybe is around 1.8 electron volt. So this is gallium arsenide, which is a direct band gap material. What about aluminium arsenide? Aluminium, the reason I am talking about aluminium arsenide also, because as I said, when X equal to 1, then the entire gallium is replaced by aluminium, then it becomes aluminium arsenide, right? So what is the band gap of aluminium arsenide? Aluminium arsenide, by the way, is an indirect band gap material. Okay, so this is 2.17 electron volt. Okay, aluminium arsenide 2.17 electron volt, and the let me just but the band which is conduction band minima, which is at the valence band maxima, that k equal to 0, that is around 3.02 electron volt. Okay, but as this satellite valley is lower, the band gap in the satellite valley is lower, it is like it will act as a indirect band gap. Okay, so you see here the band gap is 1.43 electron volt for gallium arsenide. For aluminium arsenide it is 2.17 electron volt. So if we draw for different values of X, okay, for different values of X, say this is my gallium arsenide and this is my aluminium arsenide. So in between it is Al gas, right? 1 minus X is, right? So here it is 1 point, say it is 1.43 electron volt. Okay, so I'm plotting band gap, and what is the next one? This is say 1.8 electron volt, right? And what about here? Here we have said it is 2.17 electron volt and it is 3.02 electron volt. You remember? So we have 3.02 electron volt, 2.17 electron volt. So you see here, if you increase X, okay, so see up to this it will be, so here it is direct band gap, and beyond this point it is indirect band gap. Okay, but this is not the thing what we would like to discuss, but I just thought I would like to mention this particular point. And this band gap is from where it moves from direct to indirect is around 1.93 electron volt, and the corresponding X is around 0.3, 0.4. Okay, now the thing is, what I would like to mention is, in this whole range, as I said already, in this whole range of X from 0 to 1, okay, so this is at X equal to 0 and this is at X equal to 1, this entire material of Al gas is like there is a lattice match with gallium arsenide. Okay, because their lattice constant is very close, 5.65 angstrom and 5.66 angstrom. So that is important of forming a heterojunction. Now if I form a heterojunction, I said already, or I gave you a hint, that there might be notch at the junction. Okay, that we have seen from MOSFET also. So if I have a, if I try to draw the band gap or band diagram, not band gap, band diagram. So let me say this is my gallium arsenide. Aluminum gallium arsenide, say it is N type. Okay, I'm just assuming it is N type. So this is my EV. Okay, or let's put EV1, and this is my EC. EC1, and this is my Fermi level because I am assuming it is an N type. So it is aluminum gallium arsenide. Okay, say it is N type or N plus. Say this is my vacuum level, and this is Chi1. Okay. Now what about gallium arsenide? What I am trying to do, I am trying to draw the band diagram in the using aluminum gallium arsenide and gallium arsenide to show that there will be a notch. Why the notch is important? Why the notch is important? Because we would like to have the channel in the notch or electron concentration in the notch, and at the end we would like to show you that the depletion immobile ions are not very close to that of the notch, or the density of the immobile ion is much less near the notch. Okay, so that the mobility improves. So that's the whole purpose of this discussion, so which we will discuss today and also tomorrow. So that's the whole purpose. The purpose is to increase the mobility, and the way we can achieve it, to keep the carriers in the notch. That is also true in case of MOSFET, conventional MOSFET. But in case of conventional MOSFET, there is interaction between the carrier in the notch and also the immobile ions. And here we will see how we can reduce this interaction, okay, by using heterojunction of aluminum gallium arsenide and gallium arsenide. So this is my aluminum gallium arsenide. You see, aluminum gallium arsenide has higher band gap compared to that of gallium arsenide, right? Now, so the band gap of gallium arsenide is lower, okay, compared to that of aluminum gallium arsenide. And let's assume, say it is P type, okay. So if it is P type, is difficult to draw. Let me. So this is P type. But lowly doped. So this is my gallium arsenide, and that is P minus, say lowly doped P type. Okay. So this is N or N plus, that is say P minus. So as it is lowly doped, the Fermi level is much closer to that of the intrinsic level, right? And here also, there is vacuum level, and that is Chi2. Okay. Now the thing is, so Chi1 and Chi2 is the distance between the or the energy required to take an electron from the conduction band to the vacuum level. So that's the energy. Okay. Now the thing is, if we form junction between these two, okay, then we will have like Fermi level should align, right? So for forming a junction, you remember that Fermi level should align, and also the vacuum level should be continuous, right? So if the vacuum level should be continuous and Fermi level should align, we can draw the band diagram. Okay. We can draw the band diagram like this. Let me draw it first. Then we will discuss why it is that. Okay. Okay, so this is the band diagram of that two material which will form the junction. So you see there is a notch here. Okay, there is a notch and a steep portion here in the valence band and notch in the conduction band. So this is your EG1, sorry, EG1 and EG2. So this is my band gap at aluminum gallium arsenide. This is at gallium arsenide. Of course, there is a continuous vacuum level. Let's not bother about the vacuum level at the moment. Okay, so that's my vacuum level. So how I am getting this notch, how I am drawing it. Okay, now if I have uh, aluminum gallium arsenide in both sides, you see it will be like this, right? It would have been like this, right? So this is say my N side and P side and so on, right? And on the other hand, if you instead of aluminum gallium arsenide, if we have only gallium arsenide at both P side and N side, then we have not drawing it properly. Let me. So say this is my. Let me bring it back the pen content. Yeah. So this is my. It's not properly drawn. So what I want to mean is if there is gallium arsenide at both sides, you will get like this P side and N side, right? So you see at the junction, as there is a difference in band gap, you will get this notch or you will get this steep portion, right? Now I haven't drawn it quite correctly. Uh, actually it will be something like this. Okay, why it will be like this I will come in a minute, but there will be notch. That is it understood the way I have drawn the notch? Is that clear to you, or you have doubt?
Sir,
Yes, go
sir,
ahead.
is this no, sir, is this notch occur because there is a sudden variation in chi1 and chi2? Because sir, otherwise, if
True,
chi1 and chi2 would be same, then
true.
it would be like a PN junction.
Yeah, there is a variation in chi1 and chi2. That is why this notch is coming, and this step portion is coming because there is a also difference in EG. So if you are correct, so this notch, okay. So this is if I say delta EC because the notch is in the conduction band. So we can write this delta EC equal to chi2 minus chi1 as you rightly pointed out. But what about this delta EV? Okay, since this delta EV is Eg1 minus Eg2, okay, and also there is minus delta EC. So that is basically delta Eg minus delta EC. Okay, so I encourage you to try other options. For example, you can choose P plus aluminum gallium arsenide and loaded of gallium arsenide, and you see if the notch is coming at the conduction band or in the valence band, or there is notch coming at all or not. Okay, you can also swap chi2 and chi1. So you choose two different materials. Okay, not you don't have to choose exactly aluminum gallium arsenide and gallium arsenide, because in case of aluminum gallium arsenide, chi compared to gallium arsenide, chi1 is lower. But the thing is, you can choose two materials with a different doping concentration and different chi values. Okay, of course, two material means energy gap will also be different. And you see, if you swap all these, for example, in the note I have mentioned, like here I have chosen chi2 greater than chi1, right, and Eg1 greater than Eg2, right. So you can choose other combinations also, or you can choose P type having Eg1 and chi2, and N type having chi1 and Eg1, and so on. So you can choose different combinations and check and try to draw this Venn diagram and see whether notch is coming in the conduction band or notch is coming in the valence band, or whether notch at all comes or not. Okay, so this thing you can check. I think one of the in one of the exam, one professor gave this question. Okay, so whatever we have discussed so far, he swapped these conditions of chi1, chi2, Eg1, Eg2, and so on, and asked to draw the Venn diagram to check whether where is notch is coming at all or not. Now the thing is, in this discussion I mentioned this black portion. Okay, black line I have drawn. You see, this black line is not exactly matching with gallium arsenide. Rather, it is matching with the conduction band of aluminum gallium arsenide. Right? It is ultimately matching with, because this is aluminum gallium arsenide conduction band. Right? This dotted line also aluminum gallium arsenide conduction band. Whereas this blue line is gallium arsenide. Right, this blue line, dotted blue line, and this bold blue line is for gallium arsenide. Now here you see I have drawn a black line which is the conduction band of gallium arsenide, but this is even more tilted to match this aluminum gallium arsenide. Why this additional bending? Okay, the way people explain this is, if this additional bending is not there, then even in thermal equilibrium, electron will move from one side to another. Okay, let me draw the way we draw electron concentration, okay, or electron profile. So this is my, this is how you draw electron profile. Okay, you remember, I don't know, have you gone through the Fermi distribution and all that before? I don't know. So in case of Fermi distribution, we draw like this, right? Okay, at higher, at 0 degree K, the distribution is like this. So up to Fermi level, this thing, the probability of occupying state is 1. Okay, so that's 1 up to Fermi level, you remember. Okay, but if you increase the energy, the profile changes. Okay, some electron might occupy a higher energy state, and some might there will be empty space below Fermi level, and so on. So just I don't want to go in that direction, but this profile is same as this profile. Don't bother about it if you don't know. So say this is my electron profile or electron concentration diagram in the with energy. I'm plotting it with energy. So this is my energy level, okay, and this is the electron concentration. So higher the energy level, electron concentration obviously will decrease. Okay. Now the thing is, so this is my say this is my energy level. This is my concentration of electron I'm plotting. Anyway, so what I want to say is, so this electron concentration should match in both sides. If they don't match, if they don't match, then there will be electron transfer from one side to another. Okay. Now the thing is, so this is my conduction band, hypothetical conduction band of aluminum gallium arsenide, and this is the hypothetic, sorry, this is the okay. This is basically when it is in homojunction gallium arsenide. Then this will be the conduction band. You remember, I by mistake I have drawn this blue line, or maybe intentionally I have drawn this blue line, and then I have drawn this black line just to show that there will be additional bending in the gallium arsenide side. Okay, if it is a homojunction, the conduction band of the gallium arsenide will be here. If it is a homojunction of aluminum gallium arsenide, the conduction band in this side will be here. But this gallium arsenide conduction band will bend upwards, okay, or there will be additional bending, so that at thermal equilibrium no further electron will transfer. Okay, so this is my this dotted line is conduction band of aluminum gallium arsenide, and this dotted line is conduction band of gallium arsenide when it is in homojunction. This is homojunction gallium arsenide, and this is homojunction aluminum gallium arsenide. Okay, now the thing is, here there will be additional bending, okay, and this additional bending is basically same as delta EC, because there is delta EC down, it has to go up to delta EC to match that, so that there is no additional electron transfer. So if this notch is delta EC, okay, so there should be additional delta EC bending here to match, so that there will be no electron transfer at thermal equilibrium, right? Now if you try to write the built-in potential of this junction, you remember we calculate built-in potential in case of PN junction. Okay, so if I try to write this built-in potential of this junction, it will be Vt, that is Kt over Q ln Na Nd by Ni square. You remember, this is the conventional formula of built-in potential, Kt over Q ln Na Nd by Ni square, right? Now here, so this is when it is in homojunction. But as I said, there will be additional bending to prevent or to establish the equilibrium. So the effective built-in potential in this case, in case of heterojunction, will be Kt over Q ln NaNd by Ni square plus delta Ec over Q, right? That is the additional band bending. Because of that, the built-in potential will be more. So this is for heterojunction case, right? So this is for heterojunction case, and the upper one is for homojunction case. So as I said, so the built-in potential in heterojunction is more than that of the homojunction, okay, and by an equal amount of the notch. Now this band bending, this additional band bending, which is more than that of the homojunction. Okay, in homojunction also there is band bending. You see here band bends. Okay, but this is additional, right, of delta EC. Now this band bending is gives you the electron concentration. You remember in case of MOSFET, right? The more the band bends, the more will be the number of electron in the notch, right? It becomes more N type. That depends on how much gate voltage you are applying from this metal or from this poly. Okay, whatever gate voltage you are applying, more the gate voltage, okay, more will be the band bends and more will be the number of electron. Actually, it is possible to show that the concentration of electron, okay, sorry, it is possible to show the electron concentration in the notch, okay, here, okay, that is proportional to exponential VBI over VT. VT is thermal voltage, KT over Q. Okay, exponential VBI over VT. It is possible to show the electron concentration because of the band bending. Okay, now here is electron concentration, then, okay, here electron concentration will be proportional to exponential delta EC plus VBI over VT. Okay, so electron concentration will be more. The more will be the notch, the more will be the electron concentration. Okay, now if you see carefully, this aluminum content, okay, aluminum content in will increase delta Eg. Okay, because you see aluminum arsenide and gallium arsenide, more the aluminum content, more will be delta Eg. Okay, you remember here, more the aluminum content, more will be the band gap, right? And more will be the aluminum content, means more will be band gap, more will be delta Eg then. Okay, and that will increase, that will bring more electron in the notch. Okay, that will bring more electron in the notch. Now if we can control this carrier in the higher concentration of electron, if we can control this carrier, okay, by changing the band bending. So I have this band bending. So all we would like to do, we would like to change this band bending. Okay, because the change in band bending will change the concentration of electron here in the notch. Okay, so if we somehow change this band bending, we will be able to control the amount of electron in the notch. You remember in MOSFET also we do the same thing. We apply gate voltage, we change the band bending, and that will change the concentration of electron in the channel. Okay, here we would like to do the same, but how we will do it, we will discuss a little bit later. Okay, now the thing is, let me just recapitulate. Let's recapitulate. I did mention that this concentration of immobile ions, if we manage to reduce, then that will increase the mobility. Okay, let's check the how they are related. Let's look that fast. Okay, I hope you know that, but let me just recapitulate um, what we know, because I should have discussed this before when we are discussing the motivation behind Hemt fabrication or Hemt discussion. I should have discussed, we did briefly mention the mobility effect and all that, and in case of Hemt, mobility will increase. But this mobility depends on various things, okay? Of carrier in a semiconductor depends on various things. Let me just point out some of them. One of them is lattice vibration. Okay, so the lattice vibrates and the vibration increases with increase in temperature. If you increase the temperature, lattice vibration will increase. Okay, now if there is increase in lattice vibration, that will increase the scattering of carrier electron or hole from the lattice. Okay, because the lattice is vibrating more and the electron and hole will scatter more because of the vibration. So you see mobility will degrade. So which part of the mobility? Mobility due to lattice vibration will degrade, lattice vibration component. Okay, that is one part. There is another component which affects mobility, as we have discussed already, that is like ionization scattering or scattering due to immobile ions, right? That sits underneath the channel in case of MOSFET, you remember. So this ionization scattering, how mobility depends? Roughly mobility increases if you increase the ionization scattering. So mobile, if you increase the temperature, mobility due to ionization scattering will improve. How it will improve? Because if you increase the temperature, the average energy of the electron or hole will increase, or their velocity will increase. If their velocity will increase, they will get lesser opportunity to interact with the immobile ions. If they spend lesser time in the vicinity of those immobile ions, then the mobility due to ionization scattering will improve. Okay, if we increase the temperature. So let's repeat what I said. So there are two components I just wanted to point out. One is lattice vibration. If you increase temperature, lattice vibration will increase and that will reduce the mobility. That is pretty straightforward, because then it will the carriers will scatter more with the lattice. There is another component which we are interested in this particular case, which is mobility degradation due to immobile ions. Now the thing is, if we increase the temperature, then the carrier will have much higher energy, much higher velocity, and they spend lower amount of time in interacting with the immobile ions. So at higher temperature, mobility of the carrier will increase with respect to immobile ion scattering or ionization scattering. Okay, so that is how I have drawn these two lines. So this is my effective, this is my mu effective. Okay, at lower temperature, ionization scattering will dominate. At higher temperature, lattice vibration will dominate. Okay, so it will follow the lattice vibration line, and in the lower temperature it will follow the ionization scattering line, right? Now the thing is, in case of Hemt, what we are doing, we are basically not taking care of this lattice vibration. What we are taking care of, this ionization scattering. So ionization scattering in case of Hemt is very low, because we will see in our discussion later on today, or also maybe tomorrow, that the ionization scattering in this case will be low. Okay, So if we can because what we are doing, we are basically removing the effect of ionization scattering um, from the electrons or holes by keeping them away from the notch. Okay, that we will see. So we can't do anything in as far as the lattice vibration is concerned in case of Hemt, but we'll be able to improve the ionization scattering drastically. Okay. Now the thing is, so if we reduce the temperature in case of Hemt, mobility will be very high, because at lower temperature, because we don't bother about ionization, or ionization scattering is very low in case of Hemt. Okay, so all we are interested in this one, lattice vibration. So that in that case, if the temperature, so in that case the temperature, if the temperature is low, okay, mobility will be very high. In fact, at room temperature, from gas Hemt structure, gas Hemt structure, we get mobility around 8,500 centimeter square per volt second. Okay, which is almost 8 times that of the ordinary bulk silicon electron mobility. Okay, so this is at room temperature. If we reduce the temperature, it will be much higher. Okay, so this is in the Hemt. In case of bulk MOSFET, the electron mobility is even lower. It's not even 1300. It's like maybe 500-600. Okay, so you see there is a huge improvement in case of, we can achieve in case of aluminum gallium arsenide based Hemt structure. Now how this Hemt structure looks like, let me just briefly draw it, but the working principle we will discuss tomorrow. So semi-insulating gallium arsenide, it has nothing to do with the device performance. It is we usually use to give mechanical stability of the substrate. Okay, then there will be a lowly doped gallium arsenide. As I mentioned, like we need very lowly doped gallium arsenide. And on top of this lowly doped gallium arsenide, there will be aluminium gallium arsenide, heavily doped. Heavily doped Al gas. Okay, aluminium gallium arsenide. Now this heavily doped aluminium gallium arsenide will have maybe you can say, if it is like N plus region, these regions might be N plus plus. Okay, so that we can create our source and drain. So there is a contact, okay, source, there is a contact drain, and there is a gate. Okay, you see there is no gate oxide. Okay, because it is difficult to realize oxide in gallium arsenide or aluminium gallium arsenide. So we will have, so this, if you look carefully, source and drain. Okay, at source and drain we have we have to have ohmic contact. Okay, because we don't want a lot of voltage drop in these contacts. has to have ohmic contacts. But here at gate, it is Schottky contact or Schottky contact or rectifying contact. Okay, so we don't want any current flowing through gate as usual. We want current flowing through source and drain, right? Where will be the notch? You remember, notch will be here. So this is our notch. Notch will be in the gallium arsenide side. Okay, notch will be at the gallium arsenide side, and through the notch electron will flow. Through the notch electron will flow. Okay, there is a thin this is I haven't mentioned before. There is a thin aluminum gallium arsenide layer which is undoped. Why do we need that? We will discuss. Okay, so there is a thin aluminum gallium arsenide layer, but remember this is undoped. Okay, so this is basic schematic of Hemt structure. Hemt, the name given by Fujitsu. The company Fujitsu have given the name, but there are other names like MOSFET. It is also called MOSFET. Okay, or Hemt. Hemt is given by the company Fujitsu. Okay, anyway, so this is the typical Hemt structure where we have like basic substrate is semi-insulating gallium arsenide, which is giving the mechanical stability. On top of that, there is lowly doped gallium arsenide, and on top of lowly doped gallium arsenide, there is heavily doped aluminum gallium arsenide. At two sides, if it is N plus, we will form N plus plus. Okay, much higher doping to realize source and drain. We will take source and drain contacts. There will be a gate contacts. Okay, and maybe made of aluminium, made of gold or gold germanium alloy. Okay, and this gate contact, there is no gate oxide underneath, so we have to make sure this gate contact with this semiconductor, that is aluminum gallium arsenide, will be rectifying contacts, whereas source and drain contacts with aluminum gallium arsenide, we have to make sure they are ohmic contacts. Okay, right? So they are ohmic contacts, whereas these gate contacts are Schottky contacts. Okay, now the thing is, amount of electron in the notch depends on this gate bias. Whatever bias you are applying at the gate depends on the concentration of electron in the channel, that is in the notch. Okay, now as N plus aluminum gallium arsenide is a very heavily doped, right? You see, current can also flow. Current can also flow between this N plus and this N plus through this aluminum gallium arsenide here. You see, because this is just a semiconductor bar. So if you have a semiconductor bar, say silicon, and I am basically if I have a silicon bar. Okay, so say this is my silicon bar, and I put two contacts. Okay, contacts here and contacts here. Okay, C1 and C2, two contacts, and I apply voltage between C1 and C2. Okay, so there will be current flow, right? There will be current flow because this is a semiconductor. So there will be current flow depending on the biasing. Now the thing is, here also, if you apply voltage between source and drain, current will flow between aluminum gallium arsenide. because this is, and the current will be even higher because it is heavily doped, you see. But we don't want current to flow through aluminum gallium arsenide, because if current flows through aluminum gallium arsenide, it is heavily doped, then the mobility of the carrier will be heavily degraded, because there will be a lot of immobile ions, and that will degrade through ionization scattering, that will degrade the mobility of the electron. What we want electrons only move through this notch, through this notch. Okay, if the electrons move through this notch, the mobility will be higher. Why the mobility will be higher, we will discuss tomorrow. But so what we are aiming at, we have to make sure this entire portion, this entire aluminum gallium arsenide will be depleted. If we manage to deplete this aluminum gallium arsenide entirely, okay, then there will be no current flowing through this aluminum, heavily doped aluminum gallium arsenide. So how we are going to deplete it? We will apply copper bias at the gate, which will make sure that aluminum gallium arsenide is completely depleted, and then the carrier will only flow through the notch. Okay, carrier will only flow through the notch, and the mobility will be higher. So I am stopping it here. Do you have any queries? Any doubt? No doubt? Okay, so what I will do, I will create, as I mentioned to you in the last class, I will create an assignment, okay, and you need to, I will create an assignment today sometime, and you need to draw, dump your file. Remember I mentioned that you have to write 1 to 2 page critical review of Donald's paper, right? So you write the advantage, disadvantage, challenges, or any mistake he has made when he wrote the paper conceptually, and so on. So this you need to write and dump it in the assignment section. Okay, so I will create a folder in the assignment section. You need to dump it before 12 o'clock tomorrow, before starting the class tomorrow. Okay, so I will give you time in the assignment section. I will form a folder with a time up to 12 o'clock before starting the class tomorrow. Okay, is that okay? So please do that, right? Anything you want to ask?